Suppose it's the middle of the winter on an extra snowy winter, and you, being an entrepreneur, have decided to start up a snow shoveling business. And you say, I will charge $10 for each driveway that I shovel. Well then, your neighbor down the street, he comes over and he says, I'm not going to pay you $10. I will pay you 1 penny to shovel my driveway. But, he says, more than that, shovel it each day for this month. Keep it real nice and clean. And on the first day, I'll pay you 1 penny. But on the second, pay you 2 pennies. On the third day, 4 pennies. On the fourth day, 8 pennies. On the fifth day, 16 pennies. And each day you come back, I'll double the amount of pennies I pay you. Well, you're a shrewd businessman. So you think that over. You realize that a penny is less than $10. And you say, no, sir, I will not shovel your driveway. And you turn him down. Was that a smart choice on your part? Certainly seems like that. 1 penny on day 1, that is not even close to $10. But then you go 2 pennies on day 2, 4 pennies on day 3, 8 pennies on day 4, 16 on day 5. Well, we're still really low. 16 pennies is not going to buy your milkshake on the freezing cold day. You need more pennies. Let's keep going. What about on the 6th? Okay, we're at 32, then 64, 128, 256 on the 9th day. Okay, at least I got 256. On the 10th day, I can finally buy me a milkshake. That's starting to look big. Let's jump ahead to day 31. So that would mean I took 1 penny and I doubled it 31 times. Guess how many pennies I'm getting on day 31? I am getting 2,100,000,000 pennies. Divide that by 100. That means out, Mr. Businessman. By not accepting your neighbor's offer, you just missed out on $21 million on day 31. And that's just on day 31. On day 30, you would have gotten about 10 million. On day 29, 5 million. You just missed out on about $50 million, I would say. Maybe around 40 million. Ugh, not the great business choice. But what we see there is the power of exponential growth. Exponential growth occurs at times when something doubles or triples or quadruples every time over a set time. So in this case, every day your payment doubled. So when something grows at a rate proportional to how much of it there is over set time intervals, we have exponential growth. So I could say I triple the number of pennies I give you every 2 days. So then on the 4th day, I'd have 6 pennies. On the 6th day, I'd have 9 pennies. We have exponential growth, and it grows so quickly. I could think about taking a look at my exponential growth. So on day 1, I have 1 penny. On day 2, 2 pennies. On day 3, I'm up to 4 pennies. On day 4, 5, 6, 7, 8. One more day. On day 5, I'm all the way up to 16 pennies. Take a look if I kind of plot these points where this is my days and this is my money. Look at the shape of the graph. Exponential growth has this shape to its graph where it starts off slow, but then it just shoots up super quickly. And let's take a look a little closer at graphing exponential functions. An exponential function is a function that can be described by an equation of the form y equals a times b to the x, where a does not equal 0, b is greater than 0, and b does not equal 1. If b equals 1, the exponential growth is just a straight line, because 1 times 1 to any power is just 1. Okay, we are going to be looking at kind of basic ones, like y equals 4 to the x, y equals 1 half to the x, without the multiplier out front. How do we graph these? Well, we can set up a nice XY table, and let's try and graph this by plotting some points first. So what is when x is -1, 0, 1, and 2? Let's check that out. So when x is -1, I have 4 to the -1, which is equal to 1 over 4 to the first. The negative exponent flips the fraction. So I now have y is equal to 1/4. 4 to the 0th, anything to the 0th power is 1. 4 to the first, that's 4. 4 squared, that's 16. So if I plot this, when I'm at -1, I'm at 1/4. We put that point. At 0, 1. At 1, 1, 2, 3, 4. And then at 2, I'm already off my graph, way up here at 16. Connect these with a curve. But what am I doing on the left? On the left, the graph approaches 0 but never actually touches it. Because with exponents, 4 or a number to any power is never less than 0. It gets really, really close to 0. I could go 4 to the -10th. Well, that would be 1 over 4 to the 10th. But that's not 0 yet. That's just some really, really, really small decimal point. So no matter how far I go to the left over here, I'm never going to go below 0. And that's when our graph, it's just 4 to the x. It's not shifted up or down with any transformations. So we see our exponential graphs have that nice curve where it does not go below 0, and then it at first slowly goes up, and then it just shoots almost straight up. Can we see which of these is the graph y equals 1/8 to the x power? I know that 1/8 to the -1 is equal to 8 to the first. If I flip that fraction, the exponent becomes positive, so I just have 8. What about 1/8 to the 0? That's going to be 1. 1/8 to the first power, 1/8. 1/8 to the second power is 1/64. So there, as my x is getting bigger, as I go to the right, my y value is getting lower. And that is what I see in letter A. So there, my exponential growth is not exponential growth. This is something we call exponential decay. It's getting small really, really quick. Getting smaller really, really quick. Never going below 0 though, but getting very, very small very quickly. Let's compare those two ideas, exponential growth and exponential decay. So an exponential growth function is when our base there, is greater than 1. So when our growth factor there is greater than 1, we shoot up really quickly, and it increases as we go to the right. Exponential decay occurs when b is between 0 and 1. That is, b is like a fraction. 1 over 4, 1 over 3, 2/3. It's not going to be negative. Our base is never negative in our exponential functions. But when b is between 0 and 1, exponential decay, that means as it goes to the left, it gets small really, really quick. Let's graph one more here. Y equals 1/4 to the x. So once again, we're going to graph this with a nice xy ordered pair. I'll try some x values, -2, -1, 0, 1, 2. Those are a good 5 values to try out. 1/4 to the -2. Well, that is equal to 4 squared, which is 16. 1/4 to the -1, that's 4 to the first, which is 4. 1/4 to the 0 is equal to 1. Anything to the 0th power is 1. 1/4 to the first power, 1/4. And then 1/4 squared. Well, there, I should put in my parentheses to remember that means it's 1 squared over 4 squared, which is 1/16. Square the top and bottom. So plotting these, -2 is up at 16, so again off my graph. -1 is 4. 0 is 1, 1 is 1/4, and hard to even show it, but 2 is 1/16. Connect these bad boys with a curve, doesn't cross 0, and there we see our b here is between 0 and 1, so it should be exponential decay, and that's what we see in our graph. Exponential decay gets really small as it goes to the right. Real quick, think about the domain and range of our exponential functions. Domain, that's all my x values, so what x values can go into this? Well, there is no problem no matter what x value I pick. Even though this right here, this portion of it looks like it never covers the x values over here, it does. It slowly goes kind of that way. Takes a while, but it will eventually cover all x values. So our domain is all real numbers. All real numbers can go in this function. X covers everything. And then range is our y values. So what y values does this cover? Well, as I've been saying, it never touches 0 or goes below it. Never does that. The range is all y values greater than 0. And there we practiced graphing a couple exponential functions, both growth and decay.